Welcome back, class. So, in the last chapter, we have learned about the different concepts about the introduction of the discrete time system. We have learned about the different properties, computation of the discrete time Fourier transform for the discrete time signal and the LTI systems. So now we are shifting towards the frequency domain analysis, okay, or more precisely towards the Z transform analysis. So Z transform is very vital for the discrete time signal and system analysis. Okay, so this chapter is about the Z transform. So we are going to learn about the basics of the Z transform, what is Z transform, how we compute the Z transform of the signals and the LTI system, the properties inverse Z transform and Z transform of the LTI system. Okay, so the Z transform is basically, we can actually derive the Z transform from the DTFT equations. So we know that the basic DTFT equation which we have learned last time is that we have signal and we will multiply with the minus j omega n minus infinity to infinity. Okay, so in the basic Z transform, what we are actually doing, okay, we are in the basic form, we replace a to the power j omega with the z. So it will become x of z, x of n multiply with z to the power n. Okay, z to the power minus n. So this is called Z transform. So basically Z transform is not the frequency domain. The frequency domain, okay, is the e to the power j omega, the omega domain, that is the frequency domain. Okay, but we can get, like, we can shift from frequency to Z domain. Okay, so it provides more useful information about the stability of the LTI system. We can quickly calculate the stability, we can quickly analyze the performance of the LTI system in the discrete time domain using Z transform. So this is basically equivalent to the S domain or the Laplace domain in the continuous time. Okay, we know that we shift from j omega to the S in the continuous domain using the Laplace domain. So it's equivalent to the DTFT in the discrete time domain. Okay, so if you are calculating from minus infinity to infinity, it's called bilateral Z transform, and if we are cutting from 0 to infinity, it will referred as unilateral Z transform. Okay, so for example, if we have only right-sided signal, okay, right-sided signal, for example, unit step signal, the unit step signal is only existing for the positive interval, so this is also called right-sided signal. So for the right-sided signal, we only compute the unilateral Z transform. So here geometric series representation is very important, because we are going to use this formula geometric series again and again. So we know that this will be equal to 1 over minus a, holding that magnitude of a is less than 1. This is very important throughout the Z transform. For example, we have an impulse signals and we want to calculate its Z transform. So Z transform of impulse signal will be impulse signal multiplied with z to the power n minus infinity to infinity. So here we apply the impulse property. Whenever a function multiply with an impulse, we will get the function value at the impulse location. So this is an impulse which is existing at n is equal to 0. So we will get the function value at the impulse location multiply with impulse. Okay, so it will be z to the power 0 1 minus infinity to infinity impulse. So summation of impulse is 1. Okay, so the Z transform of impulse is what? 1. Okay, similarly we can calculate. So this is another example which we will solve in the live session, another example which we will solve in the live session. So please try to get the solution for this. So I am just writing the solution here. Okay, solution of this is 1 over 1 minus 1 over 2 z minus 1. Okay, so try at home, we will solve in live. So why we are actually doing the Z transform? Okay, because we are trying to get the information about the ROC. ROC is called region of convergence. Okay, region of convergence. Okay, so in general, okay, in the last slide I have shown that, so basically if we just replace e to power j omega with z, we can get the z transform. So in general we can actually basically attach one constant here. So if we replace r e to power j omega with z, we can actually get the z transform. Okay, so here we have the z, so I just replace, okay, z with r e to power j omega. So I am replacing this because I am going from z transform to the DTFT. Okay, so this is just like this one. So and then we can take the same power x of n r minus n, okay, multiply with e to power j omega n. Okay, so the minus n power are just same. Okay, so basically this is just the relationship between the z and the discrete time Fourier transform. Okay, or we can say that this is the discrete time Fourier transform of this signal. Okay, so this is x of n, which is multiplied with e to power minus j omega. Okay, so this is just the relationship between DTFT and the Z transform. But what is the important thing here? This Z transform will exist, okay, if the summation of this signal, okay, the summation of magnitude of this signal is less than infinity. Okay, which is the basically basic definition of the stability of the system. Okay, so we can quickly calculate this thing, okay, from the ROC of the our Z transform of the signal. Okay, so basically we know that DTFT, okay, Fourier transform will exist if the system is stable. Okay, so if now if we talk about Z transform, so basically in Z transform what we do, we define a unit circle in the Z domain. Okay, this is called unit circle. Okay, and if the region of convergence, okay, covers this unit circle, okay, then our system will be stable. And if the system is stable, then its DTFT will exist. We will see very quickly that how we can actually calculate this unit circle. Okay, how we can calculate the Z transform and how we can calculate the region of convergence. Okay, so let's see the region of convergence here. For example, this is one signal, okay, u of n. So basically this is a right sided signal. So if we calculate its Z transform, so it will be 0 to infinity, because this is a right sided signal, ki power n, okay, u of n times z ki power minus n. Okay, this is the general formula. Okay, or I can write this as 0 to infinity a z minus 1 ki power n, right? So geometric series formula, 0 to infinity a ki power n 1 over 1 minus a. What is the condition? The magnitude of a should be less than 1. So this will be equal to 1 over 1 minus a z minus 1. What will be the condition? That a z inverse, the magnitude should be less than 1. Okay, so this is the Z transform with the condition of this. Okay, let me write this condition here. So a z minus 1 less than 1, or we can say that the magnitude of a is less than 1 over z minus 1. The magnitude of a is less than z magnitude. Okay, or we can say that z magnitude is greater than a magnitude. So this is the condition which must be satisfied for this case. Okay, this is very important. Now see what is actually happening here. Our Z transform is what? 1 over 1 minus a over z, right? A z inverse. Or I can write this as, if I multiply with z in the denominator and also in the denominator, so it will be z minus a. Okay, so this is more proper form. Why I did this? Because I want to draw the ROC of the signal. So let's see the ROC and the region of convergence for this case. So in Z domain, what we do, we draw a unit circle. Okay, unit circle means the radius of this circle is 1. Okay, this is my unit circle. Then I will draw the zero and poles of the z domain transfer function. So here we have 1 0 which is actually at z is equal to 0. Okay, let me use another color. So 0 is z is equal to 0. So I will draw 0 here. And here we have pole which is actually z is equal to a. Okay, so let's say the value of a. So what is the condition here? Now the condition is coming that the value of the unit circle z magnitude is greater than a. Okay, or in other word, a is less than z. So if this is the unit circle, so let's assume the value of a is, for example, 0.8. For example, so it means my pole is coming at 0.8. Okay, this is the pole location. So at the pole location, we will draw another circle. Okay, we get the pole location. We assume that the value of a is 0.8, for example, for understanding, and we draw another circle. Now we know that the value of the magnitude of z should be greater than a. Okay, greater than a. Okay, so it means we are in this region, greater than a. Okay, we are in this region. Okay, so this region, okay, this region is basically the region of convergence of this signal. Okay, outside of a, the value of z domain outside of a. Okay, so this is the pole location at a. So outside of a, this is the region of convergence of this signal. Okay, and this is our unit circle. Now if the region of, very important, if the region of convergence covers the unit circle, region of convergence covers unit circle, our system will be stable. Okay, or in other words, if the region of convergence covers unit circle, our system will be stable and its DTFT, discrete time Fourier transform, will exist. Okay, so just by getting the zero and poles and by drawing the z plane, zero and poles, we can find the region of convergence, and from the region of convergence we can easily determine that our system will be stable or not. Instead of like calculating the summation of the magnitude of the complete signal or the impulse response, from the region of convergence we can directly get the information about the stability of our system. So we will see the more examples about the ROC, and we have seen for the right hand sided, we will see for the left hand sided, and so on for the more example in the live session. Thank you very much for your time.